So now we will look at some classical theorems called the Lebesgue differentiation theorem. This is a generalization of some fact you know already on the real line. If I have a continuous function on the real line, you integrate it and differentiate it, you will get back your function. We will look at a generalization of this on Rn using averages over balls, and you divide by the volume of the ball and take the limit as the radius goes to 0, and you want to say that we get back our function f. Of course, this will be completely trivial for continuous functions, but we will look at L1 functions and more generally locally integrable functions. So that is our aim in the next 2 sessions. Okay, so let us start. We start with what is known as Lebesgue differentiation theorem. Lebesgue differentiation theorem. So just to motivate, as I said, if I take a function f, let us say from R to R, continuous, okay, then for any point x in the real line, integral over x minus r to x plus r 1 by 2 r f of y dy. Okay, so if this is x, this would be x plus r, and this is x minus r, and the length of this interval is 2r, right? So you are dividing by the Lebesgue measure of that interval 1 by 2r. This of course converges to f of x as r goes to 0 for every x in the real line. So that's a trivial exercise, okay, but this is essentially differentiating. Okay, so this is differentiating the integral of f. Okay, so in other words, if I, for example, if I define capital F of x to be integral over x small f t dt, then this is nothing but f of x plus r minus f of x minus r divided by 2r, which will of course converge to f prime of x, right, as r goes to 0, and f prime of x is of course small f of x because you integrated f of x to get capital F of x, correct. So our aim is to sort of prove something very similar. So the integral over the interval will become integral over balls, right. So you will take a point x and look at r, and so you will have something like this, right, bx or fy dy, and of course you want to divide by the volume of the ball bxr, right. So this is the Lebesgue measure of the ball of radius r centered at x, but this is, since it's translation invariant, is also measure of the ball around 0. It doesn't matter whether x or 0, as long as the radius is r, they have the same Lebesgue measure, okay, but the integral is over the ball of radius r around x. And we want to know if this will converge to f of x. Of course, for continuous functions the same proof will work, but we will prove it for more general functions. Okay, so that is what we will do. For that we define what is known as Hardy-Littlewood maximal function. Hardy-Littlewood maximal function on Rn. So we are doing everything in general on Rn. Okay, what is this? Well, so we will denote it by m for maximal function. Mf at x is equal to supremum over r greater than 0 1 by mod b0r or bxr does not matter, they have the same value, bxr. So you are looking at a ball of radius r centered at x in Rn mod f of y dy. Okay, so if this is x and this is the ball of radius r, then you are integrating mod f over this ball. Okay, so this is the ball of radius r centered at x. then you integrate mod f over that ball and look at divide by the volume of the ball. Okay, so B0 R modulus means the Lebesgue measure of B0 R. Okay, so we just use these two terms interchangeably, which of course is also equal to measure of ball centered at x of radius r. Okay, so sometimes we also use Bxr instead of B0r, but the Lebesgue measure is same, right? It's translation invariant, so it doesn't matter where the ball is centered at, you can translate it to any other point. Well, there is another way of writing this, so let us look at this guy. What is this? So integral over Bxr, let's say gy dy. Okay, this I write as integral over B0r. So this is just change of variable because you translate by x, so you can write this as x plus y, perhaps, yeah, x plus y dy, right? X is fixed, and this is, so it's essentially the convolution of g with indicator of the ball of radius r. Okay, at x or minus x depending on how this is defined, but it doesn't matter, we are taking supremum. Okay, so I can rewrite the maximal function as, which is useful, you will see that in a minute. Supremum over r greater than 0, 1 by modulus of, that is the Lebesgue measure of the ball of radius r. It is mod f convolved with the indicator of B0r, okay, at the point x. So that is what the maximal function is. Okay, so it's a supremum of convolution of two things. So the first thing is to check that it is measurable. Okay, so suppose f is in L1, okay, L1 or LP, it doesn't really matter, but we will look at L1 for the time being, L1 of Rn. Then, so this is an easy exercise. Then mod f is also in L1, of course, convolved with chi B0r is a continuous function. Okay, so let me explain this with some exercises. This is quite a useful thing to know. So let's call this as an exercise. If f is in let's say L1, you can again change it to LP if you want. G is in L infinity, then by Holder's inequality you know that f convolved with G will be in L infinity, but it's actually continuous. Okay, it's L infinity, it's bounded continuous function. How will you prove this? So hint, Cc of Rn is dense, this we know, is dense in L1 of Rn, right? So you can start with a sequence of functions Fn in continuous functions with compact support, Fn converging to f in L1. Of course, it is dense in L1 with respect to the L1 norm, right, L1 metric. Now if I look at Fn convolved with G, this is continuous, and of course this will be in L infinity as well. This is continuous because Fn is continuous, use dCt. Okay, so that's trivial. Then prove that Fn convolved with G converges to f convolved with G uniformly. Okay, but these are continuous, so the limit will also have to be continuous. So this is a continuous function. So this is a continuous function. So if I take the maximal function of f, this is supremum over r greater than 0 mod f convolved with chi B0r at the point x, correct. So it's the supremum of continuous functions. So this is a lower semi continuous function, lower semi continuous function, and so measurable. Okay, so that is very important. Even though it's very easy to establish, it's measurable because you are taking supremum over uncountably many parameters, right? So proving that it is measurable is important. Okay, so now comes the main theorem, which will tell you essentially everything about the maximal function. Okay, so consider the set E alpha. So okay, we can fix f in L1. So let me state this in a slightly precise manner. So start with the function in L1. So as of now, it looks like supremum of something and so on. It's a huge quantity, right? But it's a positive because I'm taking mod f and then chi is, these are all positive. So this is a positive quantity, but we don't even know if it is finite. It can be infinite at all points, right? So we want to say that it is not going to happen. It's quite nicely behaved function. So suppose f is in L1 of Rn, okay, then the set x in Rn such that the maximal function of f at x is greater than alpha. So alpha is some fixed quantity, okay. So then for alpha positive, you look at all those points where the maximal function is big, right? The Lebesgue measure of that, so remember the modulus of a set denotes the Lebesgue measure of that set. So this is the Lebesgue measure of the set, Lebesgue measure, okay. This is less than or equal to some constant c times L1 ohm of f divided by alpha, okay. So the constant c is independent of f and alpha. So for any f and alpha I have there is a fixed constant c such that for any f and alpha this inequality is true, okay. That already tells you that the maximal function is finite almost everywhere, because if I choose a sequence alpha n going to infinity, the right hand side goes to 0 because of this. So mf cannot be infinity on a set of positive measure. Okay, so that these are called weak type estimates. So let me tell you why weak type. So this is a weak type estimate. Okay, so that follows from Chebyshev's inequality. If I have strong type estimate, then weak type estimate will follow. So let me not elaborate on that. So you need to realize that if I have a function in L1, suppose I have a function g in L1 of Rn, okay. This we have done before, but let me repeat it. How do you estimate the set x such that gx is greater than alpha? Well, this is the Lebesgue measure of the indicator, but on the indicator g by alpha is greater than 1, right. So this is less than or equal to integral over Rn g by alpha, right. Actually over the set where g is greater than alpha, but that is contained in Rn, so you can apply monotonicity dm, which is of course equal to alpha comes out and L1 norm of g, right. So you can look at this estimate. So if mf was in L1 and it was a bounded map from L1 to L1 or a continuous map from L1 to L1, then this is easily proved theorem, okay. But the fact is it cannot be in L1 if f is in L1. So that's, I will leave it as an exercise to you. So before we go to the proof, an exercise, if f is in L1, okay, and mf is also in L1, then f is 0 almost everywhere, okay. So hint, prove that mod f of x is greater than or equal to some constant times mod x to the minus n for large x, okay. So that tells me that it is not in L1. mf cannot be in L1. So not f, mf. MF is a positive quantity, right. Okay, so this would imply that MF cannot be in L1, not in L1 unless F is 0. Okay, so that's an exercise. So now we'll go back to the proof. So let's recall, what do we want to prove? We want to prove this inequality, right? We want to estimate the measure of the set where MF is greater than alpha, right? That is what we want to check. Okay, for that we need covering lemmas. So we need a covering lemma. So this is a covering lemma of Vitali type. There are several covering lemmas which are very useful in getting estimates of this kind. So we will use one of them. This is it's not exactly the Vitali covering lemma, but it's very close to being that. Okay, so lemma. So let script B equal to, I have a set B1, have another set ball B2, etc. Bn, capital N, be a finite collection of open balls in Rn. Okay, then there exists a disjoint subcollection okay, we'll call them B again, but let's change the subscripts. So I have Bi1, let's say Bi2, etc. Bik. So each Bij is one from this collection script B. Okay, so there is a disjoint subcollection of script B, which we denote by Bi1, Bi2, etc. such that you look at the whole union L equal to 1 to n. So that is script B, union of script B's, right. The Lebesgue measure, remember the modulus here denotes the Lebesgue measure, is less than or equal to 3 to the n. So the small n is the dimension n. Okay, so it has nothing to do with the capital N. So that's an absolute constant. Okay, so this is an absolute constant depending only on the dimension. Okay, dimension is n, of course. Okay, so 3 to the n times summation j equal to, so it's disjoint, right. So the union will add up, j equal to 1 to k, measure of, so I'll let me use modulus to be consistent. So modulus Bij. Okay, so modulus of any set A is the Lebesgue measure of A, right. That is the notation we are using right now. So this says that I can get finitely many disjoint collections, so that if I make this collection 3 times bigger, it will cover the whole union. Okay, that is what this inequality essentially says, and that's what we need. Okay, proof of this is rather simple. It follows from the observation. So proof of lemma, right. So let's get rid of the lemma first, so that the remaining part can be taken up. Okay, so we make the following observation, simple observation. Okay, what is the observation? If let's say A and B are open balls, okay, that intersect each other, open balls that are not disjoint, right, that intersect intersect. So it's like, so I have A which is an open ball, and I have B which may be small, which is an open ball, okay, intersect. So one of them has smaller radius than the other, right? So it may be equal also, but that doesn't matter. So diameter of B is less than or equal to diameter of A, okay. So we are assuming that. So if A and B are open balls that intersect and diameter of B is less than or equal to diameter of A, then B is contained in A tilde. A tilde is 3 times A. So 3 times the radius of A with the same center, right, with the same center. So all that you do is you make A, so if A's center is this, then this is the radius, and then you make the radius 3 times, okay, and then look at the ball which contains that. So then B because it intersects this ball and it has smaller diameter, B will be of course contained in that ball. Most of the time 2 times the radius will do, but 3 times will surely take it, okay. So then B is contained in A tilde, which is 3 times A, okay. So you can look at intervals if you want. So if I look at 2 intervals, let's say like this, and this sort of intersects, so this is A and this is B, right, and this has the bigger radius than the other one. So if I make them twice bigger, it will be like this, and thrice bigger it will be like this, and it will of course contain the other smaller interval B, right. That is very easy to see. So it is that simple observation which will prove the lemma, okay. So let us prove the lemma. So what do we do first? Okay, so we want to get a disjoint collection, right. So first choose BI1, okay, we are naming it BI1 from this collection. So we have this finite number of balls. From this choose the one with maximal radius, right. First choose BI1 with the maximum radius. There are only finitely many, so this is possible. There may be 2 of them, you can choose one of them. Maximum radius, okay. Then, but we want a disjoint collection, so anything which intersects this will be thrown out, okay. So throw away all the balls that intersect BI1, okay. Well, that is okay because of the observation we have just done, right. Anything that intersects BI1 is contained in 3 times BI1, okay. That is what we want anyway, okay. So continue. So all that balls that intersect BI1 is thrown away. So the next one, if I choose with maximum radii, so BI2 is chosen. This is the one with maximum radius, right, in the remaining balls, because we threw away all that intersected the first chosen one, right. So BI2 is disjoint to BI1, and BI2 has the maximum radii in the remaining, and so throw away everything which intersects. Throw away all the balls that intersect BI2, okay, and continue. So I'll not bother about writing this again. So when you continue, well, it has to stop after a while because we have only finitely many balls altogether, and the inequality we want is trivially true because the union Bj, the original one, j equal to 1 to n, will be contained in 3 times Bij union j equal to 1 to k, right. So when I say 3 times, this is the this is Bij tilde, this is the ball with 3 times radius of Bij and same center, right, and same center. So if this is Bij, you make it 3 times bigger, and that is Bij tilde, right, this is Bij. And any ball will be inside one of the 3 times Bij's, because it intersects, any ball intersects one of the Bij's, right, otherwise it would have been chosen. Okay, so that will be there, and so this is trivial, and this of course implies that the Lebesgue measure of the union is of course less than or equal to sum by subadditivity sum of j equal to 1 to k measure of 3 times Bij, but we know how Lebesgue measure deals with dilation, right, 3 times bigger meaning the radius is 3 times bigger, so that is just the dilation of the ball, and this is simply 3 to the n summation j equal to 1 to k mod Bij, which is precisely what we claimed in the lemma, right. So the lemma is quite simple. Okay, where is the lemma? Yeah, all right. Right, the 3 to the n is a constant which comes out. Okay, so let us continue so that we can prove the theorem. So proof of the theorem. So let E alpha be, so we are trying to get a weak estimate, right, for the set where the maximal function is greater than alpha, right. So we want to show, so let me write down that we want to show that the measure of E alpha, right, is less than or equal to some constant times L1 norm of f divided by alpha, right. The C is a absolute constant. Okay, so constant has nothing to do with either f or alpha. Okay, so let's write it down. What does it mean to say that x is in E alpha? So recall the definition of the maximal function. M of x is the supremum of various things. Supremum r greater than 0, 1 by the Lebesgue measure of a ball of radius r, and the average of mod f over a ball of radius r centered at x, right. That is what the maximal function is. Okay, so let us write this clearly, f of y dy, correct. Okay, now what does it mean to say that m of x is strictly greater than alpha? That means the supremum is greater than alpha. So if I take a point in E alpha, that means the mesh mf at x is greater than alpha, that means this supremum is greater than alpha, which means there is one element in this collection which is greater than alpha, right. There exists bxr, right, some r such that 1 by Lebesgue measure of b0r or bxr, right. Maybe I should write bxr so that the next step will be clear. Bxr integral over bxr, that's the ball of radius r, mod fy dy is greater than alpha, right. So let's call this 1. Okay, so for each x we have a ball, right. So for each x there is a ball bx, and well maybe r sub x if you like, right. This radius can depend on x. So E alpha is covered by such balls. E alpha is covered by such balls, right. I take an x in E alpha, I get a ball around that, right. So that ball covers x. In particular, if I move x in E alpha, I will get lots of bxr's which will cover E alpha. Okay. Now take any compact set inside. So we will use regularity. Take any compact set K contained in E alpha. Okay. So since E alpha is covered by these balls, K is also covered by these balls. K is compact will imply there is a finite collection. then there exists a finite collection of these balls, right? Finite collection of these balls. So that we will name, so let us name them B1, B2, B3, B1, B2, etc. Bn, right? Each of them is some Bxr, right? R will change, of course, depending on x, such that K is contained in union Bn, right? Union Bj, j equal to 1 to n, right? Because it's a compact set, right? And you have lots of balls covering K, you can choose a finite subcover because it's compact. So now use covering lemma, use the covering lemma to get, so we get a disjoint collection By1, Bi2, etc. Bik. Remember, it's a disjoint collection, disjoint subcollection. Well, what is the big deal about the disjoint subcollection? If you make it 3 times bigger, it will cover the union Bj, right? So measure of union j equal to 1 to n Bj is less than or equal to 3 to the n times summation. Now because it's disjoint, so I can write it as summation. Okay. All right. So I know that K is contained here. So Lebesgue measure of K is less than or equal to the Lebesgue measure of the union, right, by subadditivity. Now let's look at the right hand side. Each Bij is a ball, right? So this is some ball like Bxr. What do we know about that? If I look at the measure of Bxr that is chosen so that the integral of mod f over this is greater than alpha, right? That is how we, so if you go to the first step for x in A alpha, we get a ball with this property. Okay. So the volume is less than or equal to 1 by alpha times the average, right? So use that. So this tells me that the volume of Bxr is less than 1 by alpha times the average mod Fy dy, right? So apply that here. So this is less than or equal to 3 to the n, there is an alpha and there is summation j equal to 1 to k, and I have integral over Bij mod Fy dy, right? Each Bij is one such Bxr, so this works, but these are disjoint, right? So these are disjoint, so when I sum up it becomes the integral over the union. So this is 3 to the n by alpha, 3 to the n by alpha, and integral over union Bij, right, j equal to 1 to k because of disjointness. Mod f is positive, right? So it's disjoint, and which is of course less than or equal to, so union B, instead of this I can replace it by Rn, right? So I have 3 to the n integral over Rn mod Fy dy divided by alpha, right? This is what I wanted. 3 to the n is some constant, L1 norm of f by alpha. And so this is true for any compact set K, right? So if I look at the compact set K, so where did we start? Take any compact set K contained in alpha. I have the estimate that the Lebesgue measure of K is less than or equal to 3 to the n L1 norm of f by alpha. So this implies by regularity, right? By inner regularity, I can take supremum over K contained in E alpha. I will get the measure of E alpha, right? That is less than or equal to 3 to the n L1 norm of f divided by alpha. That's precisely what we wanted to prove, right? This is the theorem. Okay. All right. So as a simple corollary, we get simple corollary is that the maximal function, if f is in L1 of Rn, then the maximal function mf is finite almost everywhere. Okay. So, even though we are taking supremum over averages of mod f over balls and things like that, the maximal function is not too large, it is finite almost everywhere. Okay. So, we will stop here. So, we just defined the maximal function, this is called the Hardy-Littlewood maximal function, and we proved a weak type estimate for that. The measure of the set where the maximal function is greater than alpha is controlled by the L1 norm of f divided by alpha. That is the essence of what we have done. We will use this in proving that the averages of f for a locally integrable function will actually converge to f almost everywhere. So, that would be the aim in the next session. Okay. So, we stop here.